In this video, we're going to take a deeper look at the SIR model for disease modeling. If you haven't yet, we do have a previous video in this playlist about the basic conceptual ideas for this model, so take a moment to check that out or look up information about what the SIR model is yourself. Again, I'll start with the disclaimer that I am not an expert in disease modeling, I'm just sharing what I do know. So, we've got our SIR model. We're saying that for the disease that we're studying, we can reasonably model this as everybody starts out in this pool of susceptible people. That would be the S here. Once people or individuals contract the disease that we're studying, they would move to the infectious pool. That would be where they would be capable of spreading the disease, and then eventually they would recover, or those who have been infectious but have now ceased to be infectious would move to the recovered pool. And in this model, once you're recovered, you stay immune, you're no longer susceptible. So, analyzing this, we should begin with a few pieces of notation. So, in particular, we're interested in rates at which individuals move from one compartment to another. So, I'm going to call beta the, it's not precisely a rate of movement from here to here, but it would be an average number of contacts, adequate contacts. So, if someone is infected and they're interacting with a bunch of people closely enough that the disease could be transmitted, how many people on average would each person interact with before somebody actually catches the disease? And so, either like super infectious disease, that would be a fairly small number of people until somebody else catches it. If it's not a super transmissible disease, then you might end up interacting with a lot of people before one person catches it as well. So we've got that. Gamma is going to correspond to recovery, so can think of it as a recovery rate. Maybe more precisely, we could say that 1 over gamma is going to be equal to the time to, I guess, the infectious period. How long a person with the disease can continue spreading the disease. So we've got those two things, and then we're going to say that N is going to be the total population. And we're going to assume that everybody in the population falls into one of these boxes, so N would be equal to S plus I plus R. And I probably should insert that all of these we're keeping track of as functions of time, so the number of people who are susceptible at any given time, and then infected at any given time, and then recovered at any given time. So with all of that, we can set up a system of differential equations. So how quickly the number of people in the susceptible category changes. People are just going to be, I guess the only change that's happening is that people are leaving the susceptible category, going into the infected category. Gamma has to do with that. So anyway, but so we're just going to be, in this model, number of people who are susceptible is just going to be decreasing. Again, we had this beta as average number of adequate contacts for transmission. That said, we also kind of need to keep track of how likely it is that you're going to run into an infected person. If there aren't all that many people who are infected out there, or infected individuals, then you're not as likely to have adequate contact with somebody infected for transmission. And then, if there are a lot of people who do already have the disease, catching it is just more likely because there are more people around who are capable of spreading it. So we're going to, in order to get a measure of that, multiply together the number of people who are susceptible times the number of people who are infected. That gives us some sense of, on average, how often susceptible and infected people or individuals, again, if you're studying animals or something, this might not be people, but for shorthand, anyway. Multiply S times I to get a sense of frequency of adequate contacts for transmission. We'll multiply that by beta. That would then say, okay, if you've got an adequate contact happening, how likely is it that the disease will actually jump from the infected person, the susceptible person will also contract the disease, and then divide that by n, since that's an average number. So we've got that. That would give us precisely how quickly individuals are moving from the susceptible category to the infected category per period of time. I prime, because we've got people leaving the susceptible category at this rate, they would, I guess, also be entering the infected category at the same rate, because that's, for this particular disease, the only path that you can go down. So we would have beta times S times I. Recopy exactly what I had here. And now that's recopied, I can erase the circle around it. And then we've also got people leaving the infected category and entering the recovered category, so that we know you don't need to be in contact with recovered people in order to recover from a disease that's really just going to be multiplying our recovery rate by the number of individuals in the infected category. So we'd have gamma times I, that would be the rate of people. Gamma, essentially, recoveries per individual over a period of time is what the units would be, because here it would be, for each person, individual time for a recovery to happen. So yes, we would multiply that and get how quickly individuals are moving from the infected to recovered compartment, and then recovery, again, people are moving at this rate, and so that would be the rate at which individuals are entering the recovered category, but it would be positive, and it would also not be written in red, unless you really want to. So that would be our model. There are a few things to observe. So I guess first, we had this equation here that the total population was equal to S of t plus I of t plus R of t. Just doing a little bit of calculus, we're going to see that here n prime of t is going to be equal to, just because derivatives are, and we can say this now that you've seen some linear algebra, a linear we'll say a linear transformation, but linear operator. Anyway, you can split up derivatives over addition. That's the thing that you've known since calculus. Total population, for this model, we're assuming that it's not changing. We're not worrying about longer time periods where, the population itself is shifting. So population rate of change should be 0, which in other words would mean that these should all cancel one another out. So you can actually see that over here. So for example, r prime of t should be equal to negative s prime of t minus I prime. And if we look at our system of equations, if we were to do negative s prime minus I prime here, we would get r prime here. So in other words, this r prime, it doesn't really add any new information to our system. Everything that we need to know is already encapsulated in s prime and I prime. So we can reduce down to a system of just two equations. As we've written it here, we have our s's and i's only in the top equations, and so we don't even have any r's showing up. We could use this information here if we had any r's to rewrite them in terms of just s and I. So really we just need the top two lines of this system. And another thing that we often do is normalize. So just for convenience, we assume that n is equal to 1, and then s and I and r represent fractions of the population. That fall into each category. So, we'll rewrite that for this video. I'm going to switch from capital S's, which was like the total number of people susceptible, to a lowercase s, which would represent the fraction of people who are susceptible. So lowercase s prime would be equal to negative beta times lowercase I prime is not the imaginary number. Well, actually, first I should write an s, but even if it's coming second in what I'm writing down, lowercase I here would be the fraction of people who are individuals who are infected, and then this n became 1, so I can start ignoring that, and then I prime is equal to beta times s times I minus gamma times lowercase I. So we've got this. We can do some analysis right now. So typically, if we're looking at these systems like this, we'd be interested in looking at equilibrium values. Here things are a little bit different just because, for example, s, clearly, if s prime is 0, that would mean that either s is 0 or I is 0. I being 0, nobody actually is infectious, so the disease isn't spreading, nothing is changing, so that would be a trivial equilibrium solution. Otherwise, the only other option is that there's nobody left who is susceptible, and so that's also, a valid equilibrium state, but doesn't really tell us all that much about the system. So in order to get the information that we want, I'm going to look at just focusing on I prime being 0. So just when we've got a steady, steady number of individuals infected. So if we factor this, we've got that I prime is equal to I times beta s minus gamma. So clearly, as mentioned, if I is 0, nobody is infecting anybody, we stay at whatever numbers we were at, but we've also got this beta s minus gamma being 0, so s is equal to gamma over beta. So that would be another state where if the number of susceptible individuals is right at that point, the number of infectious individuals would be in equilibrium, at least briefly. At least, S prime would still be negative, so there would still be some push to new infectious individuals, but it wouldn't be coming from the I prime derivative would in fact be at 0 there. So we have that, that's a brief moment where things are kind of in balance somehow. So, this is an important quantity. We're going to actually look at beta over gamma, or if we think of it as beta times 1 over gamma, where 1 over gamma was the length of time an individual is infectious for. So this is the basic contact number, so somehow we're multiplying together how likely an infectious individual is to infect new individuals, and also how long an infectious individual is infectious for, combining those two into one quantity. For this system, if we look at S sub 0, so like the initial number of susceptible individuals, I'll just write that as S sub 0 so that it's clear, times this sigma. If that's less than or equal to 1, we end up seeing that our disease is going to end up dying out. We'll have that I of t decreases to 0. So for our S value, and we know that multiplying that through, like if, we had divided through by gamma here, we would end up with negative values for that I prime, and so the number of infected individuals just keeps on decreasing. On the other hand, if F's of 0 and susceptible individuals is always decreasing, and so our numbers just go down. If it's greater than 1, we start off increasing, and then goes back to decreasing to 0 for this particular model, because there's no recovered people going back into the susceptible pool. So if nothing else, either the disease, we start off with the people who are the individuals who are infected, they cause whatever new infections to happen, but it's not happening quickly enough, often enough that the disease takes hold. That would be the first case. If we've got that there are too many new cases per infected individual, then we would spike, the disease would more or less progress through the entire population, but then as we filter people from the susceptible pool through to the recovered pool, we don't really have enough people left that are susceptible to the disease to be an issue. Really, if we're looking at ways of addressing an infectious disease, though, we'd rather be in the first case, so we'd rather look at means of either decreasing for infectious individuals, like the number of contacts or the transmissibility of the contacts. So, thinking about back to COVID stuff, doing things like having people social distance or masking. Something like vaccination would also reduce that it usually probably would include it in its own pool in the model, but that would at least do something to reduce the pool of susceptible individuals. But then also, if we look at medical intervention, that would reduce the amount of time that it takes to pass from infectious to recovered. That would also help with that quantity. Something I remember there were questions, for COVID, is it better to just, get that immunity built up in the population by having people pass through it? But, there are also long-term consequences, long COVID type things, where it probably would be better if we have the first case where the disease dies out without touching the full population, as opposed to just having it kind of pass through everything at the start. That would have been something that was still worth pushing for. So again, this is one model. Other models, there are definitely equilibrium states where you could have the disease kind of being present, hovering in the population, and you want to look at that. But at the very least, we've seen a little bit how you can create systems of differential equations out of these. Join us for the next video where we attach some numbers to these things. Thanks for watching.